Okay, it's good now? Yeah. Okay, hello everyone. My name is Fernando. I'm from QCrew, a group in QED. And in this talk, I want to talk about how we have been working to expand the power of superconducting circuits to emulate light-matter interactions. In specific, I will show how we made a new device that we can use to switch between light interaction regimes and use that for quantum information processing. So our motivation is very clear. We are interested in light-matter interactions because they're still at the center of physics research. For example, at quantum technologies to manipulate single excitations in trapped ions using optical lasers, or to manipulate spins in energy centers using microwave radiation. And besides technologies, we also are interested in research topics, frontier research topics, such as flow-band engineering for manipulating the electronic band structure of crystals, or the creation of light-matter hybrid excitations, such as Moorhead polaritons. In bosonic circuit QED, we emulate light-matter interactions for quantum information processing. So this is a typical device where we have a superconducting cavity that is basically a light field, and we have coupled to it a transmon qubit that emulates electronic transitions of an atom. With these ingredients, we can already do tasks such as quantum error correction and metrology, and by using the cavity as a data storage and the transmon as a control device. So this system, it can be described by a quantum Rabi model, Hamiltonian, with a coupling between them characterized by the coupling factor G, as you see there, which is basically a electrical dipole interaction. And we work in the regime where this G is much faster than the losses, so it can have coherent communication between the elements. And what we're going to talk about is that this Hamiltonian, even though it's relatively simple, it still holds a lot of nuance, especially when we consider different detunings between the cavity and the qubit. For example, if these elements are resonant, that is the detuning 0, they are able to coherently exchange excitations between them, one from the other. And these oscillations, they're quite fast, so they're actually a great resource for creating test gates or state preparation. But the problem, as you can guess from here, is that the data storage will be sharing a lot of its energy with the control device, which is not great. It will introduce the coherence, and it's not going to be very long-lived anymore, right, your data. So we don't usually use it in practice, the regime very often. However, if we detune it more, by let's say 4 times G or more than that, then our Hamiltonian becomes a dispersive Hamiltonian, which suppresses oscillations, but they still communicate through this dispersive interaction, which works basically like this. If you excite your qubit, your cavity frequency will be shifted by a value of chi. So with these interactions, we can still do control, fast gates, everything, universal gates on your system. But even though it's really good and very useful, there's still some problems, specifically when you go to high order correction of the interaction, where current nonlinearities start to show up in the system, which are often a limiting factor in protocols. So there's a lot of research to keep the current nonlinearity down and just get the nice part, which is the control. But I'll tell you right away a very simple way of getting rid of the nonlinearities, which is making a transmon that is simply completely decoupled from the cavity. Then yeah, you'll have no interaction, you have no distortion, but you also have no gates. If you have to choose one, and that's often the case, you have to choose one of these. Which one we get? We go for the dispersive one, because it's a good compromise between control and protection. But our question is, what if we can use all of these regimes at once? We could pick the ones we can switch between them, right? We just pick the good things and leave the bad things behind, or suppress the bad things. So that's what I'm going to do. In principle, this can be done by using a flux tunable transmon. That is, you add a control line that can generate a magnetic field and bias the transmon frequency. So you can just tune whatever you want. But we also have a few requirements. The first one is that this extra control cannot add decay to the cavity, so it cannot destroy the data mode. It has to be easy to integrate into superconducting structures, which is not a given. It's an engineering challenge. And it needs a fast response. That is, the switching of frequency needs to be fast enough so you can do within the same experiment. So having a device that checks all our wish list is not so simple. And it was actually already tried before. sadly often comes at the cost of reducing the cavity lifetime. So that's our challenge, introducing flux tunability to access these light interaction regimes without destroying the cavity lifetime. Our suggestion is to use a magnetic hose, which actually I presented here before, the intermediate project that we had, which was a paper that was published that proposed a magnetic hose as a way to introduce magnetic field for inside superconducting structures. So this picture shows a half-open view of the hose, which is a cylindrical structure made of alternating layers of mu metal and aluminum. It's basically, in a nutshell, it works like a metal material that propels a magnetic field forward, only along this axis. So you can make a small coil that has a fast response, but on the input side, and then put a transmon on the output side where it's going to receive the field, right? And a very nice feature of the hose is that the output part is a built-in filter. So the fields from the cavity and the qubit, they are filtered and they cannot travel back on the hose and decay. So this is how it would look like in our device. That's our design. We put the hose right on top of the transmon and try to distance them, the transmon and the hose from the cavity as much as possible to protect its energy. So it seems like the hose can give us all the features, all the nice features from a wish list. But in practice, it actually took a lot of effort because the hose has some very perverse requirements that makes it very difficult to fabricate. For example, the aluminum layers, they have to be as close as possible, and here we're talking about 0.1 millimeter, and they cannot touch, otherwise you create superconducting loops that block the magnetic field from going through. And we also want to pack as much magnetic field as possible, so we create a magnetic coil, we create a coil under the microscope and try to pack these wires as closely as possible, as we can. So it took a few months, a lot of effort to create, to perfect this recipe, but it was worth the effort. Once we pulled out the device, the first thing we did was to do a spectroscopy experiment to check its frequencies. So here you can see on the graph on the left, as a function of the current on the coil, that you have a flux tunable transmit, that's the frequency going down, that is crossing the cavity frequency that is still. So they show an avoided crossing with an interaction, which indicates an interaction complete factor of approximately 7 megahertz. And more than that, we also see here in the graph on the right, that you can enact these changes of frequency really fast. So by applying flux current pulses, step pulses, we can measure the frequency of the transmit over time, and we see that the response is under 16 nanoseconds, which is much faster than the coherence rate of our system. So that means we can use this within the same experiment easily. And more importantly, we measured the cavity lifetime, and we found that its lifetime is roughly 150 microseconds. There was some variation from cooldown to cooldown. We sometimes got even higher lifetimes, but this value is already very good for a good chunk of protocols in quantum information processing. So we had overcome that barrier from the previous experiments. This graph also shows how we can go through different regimes that we talked about before as a function of the detuning delta. So you can go from the resonant regime on the left to the decoupled, going through the dispersive regime in the middle. Here I make an extra distinction where you have the strong dispersive regime where the dispersive shift chi is higher than the line width, and the weak dispersive regime where the shift is lower than the line width of the qubit. They are qualitatively different, as we're going to see in a minute. So another question is, we have the device that we aim for. What can we use it for? How can we use it for quantum information processing tasks that are useful? So in the first experiment, I want to show how we can do fast shift preparation using the resonance regime. This is a vacuum Rabi experiment where you can see oscillations that indicate a photon swapping back and forth between the transmon and the cavity as a function of the detuning between them and the interaction time. We can see that if we stop the experiment on the first 25 nanoseconds, we will load all the energy into the cavity, effectively preparing for state 1. And for reference, this is very fast because it's roughly at least 20 times faster than normal optimal pulse protocols. And the way we apply this is also very simple. Just following this diagram here. Just consider the diagram on the top. The way you do it is you start with them detuned, they come to transmon and cavity. You excite the transmon, and then you bring them into resonance to load the photon. If you want to load the Fox state 2 or 3 or higher, you can just keep repeating this procedure over and over. So it's very analytical, there's no numerical pulse involved, and it's very fast. So quite useful. So now that we prepared the state, we want to verify we actually prepared it. So we're going to do tomography on the cavity, and I'm going to split the experiment in two. On the first part, I'm going to detune the qubit to the strongest pulse regime and do a parity mapping to get the Wigner tomography of the cavity. On the second experiment, I'm going to detune it more. So we're going to leave the strongest pulse regime and go to the weakest pulse regime. Here we cannot do parity mapping anymore because the interaction is weak, but we can use conditional displacement gates to measure the characteristic function, which is the Fourier transform of the Wigner. So it's you get another function, but it's equivalent because one is the Fourier transform of the other. So what we have is that measuring this, both tomographies from Fock state 1 and 2, we have verified that you can not only prepare with good Fock states, but you can also choose which tomography and do high quality tomography. So what this experiment tells us is that even though both tomography techniques, they pertain to different interaction regimes that are mutually exclusive, now that we can switch between them, we can choose whatever one we want. Be it because we want to access a specific type of information from the system, or because one of the protocols is more resilient to noise, which is actually what you can see here. The characteristic function in our case is a bit less noisy. That's because it uses echo pulses that are more lenient with low T2s. So it's really like up to you. You have the option to do it if you want. In the second experiment, I'm going to show how I can then suppress the non-linearities by accessing the decoupled region. And let's start with curve. So what I do, how I show this, is first we prepare a coherent state on the cavity, and then wait for it to evolve for 10 microseconds. At the end of this wait time, we measure the characteristic function. And we're going to repeat this for 2 points. The first one of them, the curve is 6 kilohertz, which is a typical value that you can find in the literature. It's very common to see this value being used. On the second point, we're going to suppress by detuning, and the curve is going to go down to 0.09 kilohertz. So the tomography shows that, indeed, if you detune more and reduce the curve, the characteristic function of the coherent state still preserves the fringes that are known, that are characteristic of a coherent state. They indicate the phase of the coherent state. However, if you do the same experiment at a high curve, these fringes are going to spiral around the center, and it's going to completely distort the state you want to distort information, and it's not as useful anymore, right? Now we can go one step further and suppress the dispersive shift between the cavity and the transfer. Here we do a very similar experiment, but during the wait time, we're going to be kicking the transfer by applying pi over 2 pulses. And these pulses, they will then shift the cavity frequency back and forth, and it's going to induce dephasing. We're going to also compare 2 points, normal value, a typical value of 1 megahertz for the chi, and a more decoupled of 0.05 megahertz. And the tomography, once again, shows that for more decoupled, there are some distortions. Okay, we have some rotation, some dephasing, but you can still see there's a coherence, and you can still see the direction of the phases. On the other hand, when the chi is higher, we have complete dephasing of the cavity state. There's no direction of the fringes anymore. There's no phase. So, in this talk, I showed you how we created a new device that can switch between light matter interaction regimes, and how we can use that for tasks of interest in quantum information processing, be it fast state preparation, versatile tomography, and suppression of non-linearities. And I would like to thank my group for this work, and also for our recent publication with these results. And I would like to open the floor for questions.